Log on, tune in, find out. Another good idea from Cambridge.
Start out with Martina Vandebroek from the Catholic University of Leuven, who will be talking about estimating the heterogeneity distribution of willingness to pay using individualized choice sets.
Thank you for the introduction, and thank you for inviting me. So I will talk about the sequential design of choice experiments. I must admit that this is the same talk as I gave in the International Design Conference in Memphis last May. So some people will have heard this before. I've changed a few slides a little bit, but you can try to find out what I've changed to keep you busy. Okay, this is the outline of my talk. I will say a few words about willingness to pay, and how we can use choice experiments to estimate willingness to pay. And then I will say a few words about the law of heterogeneity. People are different, so they have different willingness to pay values, which complicates the design problem very much. It complicates the design problem so much that we cannot really solve it, so we have a way around.
Turn on the mic, please.
I've not switched it on. I've put it on, but not switched it. Haven't you heard anything of what I said? So I can just go on. Sorry? So our solution is to look for individualized designs, optimized for each person separately. I will show you some simulation results to show that it works very well. So what is willingness to pay? As you can guess, I guess, it's what you want to pay for some attribute or to avoid something. And you can find applications in a lot of different areas. Here are a few examples. For instance, in marketing, they try to find out how much people want to pay extra for a 1-inch larger screen in a laptop, for instance, or a larger hard disk. They use it a lot in transportation studies to find out how much people want to pay extra for a travel time reduction. Then they call it differently, but it's willingness to pay, essentially. There are some other examples, but you can find a lot of different applications. So how do you measure willingness to pay? Until some time ago, they just asked people how much do you want to pay for a screen that's 1 inch larger. What do you want to pay extra? Now it turned out that you get very unreliable results like this because people are not used to making this type of decisions. So nowadays we use utility model to derive willingness to pay values. So this is totally wrong. So if you assume that you can measure the utility, or you can model the utility, that's the appropriate word, as a combination of what each attribute is worth for a person. So for instance, in the laptop case, this stands for the size of the screen, and this is what the worth the value that people attach to this size of the screen. Same for the hard disk, same for the price. If you can model the utility that people get from some product in this way, you can also derive the willingness to pay as a ratio of 2 of these coefficients. So you try to find out how much the price should change for a change in the attribute. That's basically it. So that's what you want to estimate. So if in case you can estimate the betas, you can also estimate the WTP. Now how do you estimate the betas in the utility model? That's where the choice sets come in. You give people a choice set like this. For instance, if you want to find out how much people want to pay extra for a larger screen or a larger hard disk or whatever, you make choice sets like these. You let people choose their preferred laptop. That's something people can do, reliable, because that's what they do in the shop. They see different computers and they have to choose between different products. So that's a reliable choice. And you give them different choice sets like these, and from this you can derive the beta values in the utility model. I'll show you how. With the appropriate assumptions on the utility model, you can show that the probability that some alternative k is chosen as choice set S looks like this. It has the utility of the product itself and of all the other products in the choice set. So if you have all the choices that were made by the person, you can look for the maximum likelihood estimates. This is likelihood function. You just optimize this, you get values for beta. And from the betas you can derive willingness to pay. Okay. Now we are here in a design conference, so what's the design problem? You want to, so next slide, you want to know what profiles or what computers to show to the people, and what profiles, what laptops, which laptops to combine in a choice set, such that the information on the betas is as precise as possible. Okay. And in this case, the information matrix can easily be written down. So you can just optimize the information to get the best information about the beta. Well, this has been done for this model in a local optimal way, in a semi-Bayesian optimal way. So, but now we will complicate the model, the problem a little bit. What I showed you before as an introduction was this utility model, where I assumed that all the persons had the same beta vector. So they all attach the same value to a larger screen, a larger hard disk. This model was used for a long time, but nowadays people use more sophisticated and more realistic models, like this one. It's a random coefficient model. So now we model the utility in a similar linear model, but now the beta n's come from a distribution function. So each person has a different beta n. Okay? And now the main goal is to find these parameters. What is the mean willingness to pay? No, that's not willingness to pay yet. What's the mean value that people attach to some attribute level? And how different are people? That's what's in the sigma. Okay? So this is a heterogeneous market. People are different, and you try to model the difference too. Okay, what's the consequence for the estimation and the design? You have a similar expression for the probability that some alternative is chosen in the choice set as before. But the likelihood function now is much more complicated because you have the multivariate integral here. It's so complicated now that maximum likelihood estimates are very hard to compute, so people mainly use hierarchical Bayes estimation. That's what I explained here, but I will skip this, that's not that important. So you have much more problems in estimating the model. But then if you look at the design problem, what choice sets should I show now to the people to get precise information about the mu beta and the sigma beta? Remember, the information matrix is minus the expectation over second derivatives of the log likelihood. This is now the log likelihood. If you compute this, you get an horrible expression, and the main problem is that the observations do not are not simplified. You cannot get rid of the y's here. So you get a multivariate integral here, and then an expectation over the y's, which cannot be simplified. So you have to use simulated responses in the criterion. So it's a very hard problem to get optimal designs for this model. There are some results by Bleemer and Rose who computed local optimal designs for this model for very small cases, for very small choice set and only a few attributes. So as this is a very hard problem computationally. It's not that it's hard to understand what has to be done, but it's almost infeasible to compute the optimal designs. We have looked at another approach, the individual adapted sequential Bayesian designs. And so what we do here is not looking for just the optimal choice sets that you have to show to everybody. We try to get very good choice sets for a particular person, to estimate each beta n very precisely for each person separately, and hoping that in the end, if you can estimate these different beta n's very precisely, you can also estimate the distribution function rather precisely. Okay. So how do we get optimal designs for each individual separately? That's what's explained here and on the next slide. Ooh, sorry. So we start from some prior distribution. So this will be some idea about the heterogeneity. Okay. And then we look for a few choice sets that are optimal for the conditional logic model, so the homogeneous model. Not heterogeneous, but homogeneous model, the conditional model. So this is not really optimized for this person because we don't know anything yet about this person. We only have this prior distribution. Okay. So we look for a few choice sets that are optimal for the conditional logic model with this as a prior on the betas. Okay. Then we give these choice sets to the person. He makes choices. He chooses his laptop in each of the choice sets. And then we update the prior distribution with these choices to get the posterior distribution on the beta n. So then at least we have some information about this particular beta n of this person. And with this information, we use then this posterior density as a prior distribution to set up the next choice set. So in the next choice set, now each choice set is optimized separately. So we look for the next choice set, called xi plus 1, so that the combination of the previous choice sets and this new choice set is optimal with the posterior distribution that we had on the previous slide. So this is the best information we have about this particular beta n. This is posterior from the previous step, but we use it here as a prior distribution. And we use here the generalized Fisher information, which is based on the posterior too, instead of the normal Fisher information matrix. So then we get one new choice set. We give it to the person. He makes a choice, and we update this prior with this new choice. And we have a new prior, a new posterior, which is used as a new prior to construct the next choice set. Okay. So the first few choice sets are not individualized because we don't know anything about the person, but as soon as we can have a little information about this person, we sequentially optimize each choice set. And so in the end, we have for each person individualized choice sets and responses, and then we put them again in hierarchical Bayes estimation to estimate the mu beta, the sigma beta, and get better estimates for beta n. Okay. So that's an approach that works well. We have shown this to estimate the betas. Now remember, one of the first slides on the title says I'm looking for the distribution function of the willingness to pay parameters. Now what people have been doing is from the distribution function that you get on the beta m and the beta p, look for the distribution on the willingness to pay. But of course you get problems because you have this ratio and beta p. Well, people have thought of different solutions. They keep beta p fixed, for instance, and have only random coefficients for the other coefficients. Or they use distributions that stay away from 0. But even then you get a lot of problems with this distribution. So although this is a very good way to get distributions for utility parameters, beta, you still get problems to find the distribution function for the willingness to pay parameters. So we then adapted this approach, is an individualized approach, to estimate the WTP parameters, and therefore we use a trick I have presented here on the previous DEMA conference, but then for homogeneous markets. A trick to get the distribution function of the willingness to pay values is rewriting utility function. So this is the original utility function with person dependent betas. What you can do is multiply and divide each parameter by the price parameter, and then you have an expression in the WTPs and in the price parameter of everybody. And then we can follow the same logic as before. Look for individualized designs that are optimal for estimating the individual willingness to pay parameters. And from these then derive the distribution function of the willingness to pay. I will not go through the methodology again. The main changes are in the design criterion that has to be changed a little bit, and in the hierarchical base estimation. But I will mainly show you that this works quite well with simulation results. So I have a small design setting here. We did the same thing with a large design setting, but you get similar results. So you assume you want to give every person 12 choice sets. And we will optimize the last 8 ones, but the 4 first ones are not optimized for each individual separately. Okay. In each choice set we have 3 alternatives, so for instance 3 laptops to choose from. And each laptop is described by 4 attributes that have 2 levels, for instance. And we consider 100 respondents. Now we have to generate data and generate design, so we need some prior distribution. This is the prior distribution on the willingness to pay parameters and the price parameter. Numbers are not that important. They come from a case study in the literature. We consider, in fact, 4 different settings. You see a coefficient here and there, and we have a low and a high value for small a and a low and a high value for sigma. And what does it indicate? If a is small, it means that the mean values for the willingness to pay and the price are small. If these parameters in the utility model are small, it means that the error term is very large and that you don't get much information out of the choices that are made. So if alpha is small, it's called low accuracy, because if the parameters are small, the error is large. Okay, and then you don't get very reliable information out of the choices. So if the A is large, the coefficients are large, the error term is relatively small, and the choices are very informative about the parameters of this person. Same thing, well, similar thing with the sigma. This gives the heterogeneity between the people. So if sigma is small, the people are not very different. If sigma is large, the people are very different. Okay? So I have 4 combinations, low and high accuracy, low and high heterogeneity. Okay, I will compare my individually adapted sequential designs with 3 other designs. The first one is an orthogonal design, or an almost orthogonal design, because orthogonal design did not fit in this setting. That's what people often use, and it's easy to show that this is an optimal design if all the parameters are 0, which is called utility neutral design. And then we have 2 semi-Bayesian optimal designs for the conditional logic model. So we can solve the problem if there is no heterogeneity in the market. And then we can compute semi-Bayesian designs that take into account uncertainty about parameters. So we can use our prior information that we need anyway to get semi-Bayesian, the optimal designs for the conditional logic model. First, we only did these two to compare our designs with, but then the referee said that we had better results not because of this clever approach, but because we give different people different designs. And then you get more information than from giving just one design to everybody. Okay. So what we did as extra is having several optimal designs for the conditional logic model. So optimized for a homogeneous market, but then you have different equivalent designs, equally good designs, and we gave those to the individuals. So that's what I call here the heterogeneous design for the conditional logic model. And this should convince you that it works quite well. These are results for the low accuracy and low heterogeneity. This is the worst scenario for our approach, because if you have low accuracy, it means that the choices that you get are not very informative. And if you then base your next choice set on this information, perhaps you're not really going in the right direction. And if you have low heterogeneity, it means that all people are more or less the same, so why using an individualized approach? What you see here are the posterior distributions of the first willingness to pay parameter. So I know what the willingness to pay parameter is. The mean first is minus 0.4, that's where the line is. With my approach, well, with all the approaches, at the end we estimate the mixed logic model with the hierarchical Bayes approach, and we get posterior distributions for all the parameters, also for the mean willingness to pay parameters. And the red one is posterior distribution we get with our approach. I think it does pretty well compared to, for instance, the orthogonal design, which is really off. And you find the homogeneous and the heterogeneous designs for the conditional logic model. They are both equally bad, I would say. So it seems to work very well. Now we have not just one parameter in the mean, we have a lot of parameters in the mean. So averaged over the different parameters in the mean, you get the root mean squared error here for the low case. So low accuracy, low heterogeneity. So this is a summary of what you would get on the previous slide, but then for different parameters in the mean vector. So this is the result for the low accuracy, low heterogeneity, low accuracy, high heterogeneity, high accuracy, low heterogeneity, and high accuracy, high heterogeneity. And whatever the situation, it outperforms the other approaches. This is for the mean vector, the mean willingness to pay in the market. This is the same information for the covariance matrix. And here too you have outperformance of our approach. And also for the individual beta n's, we also estimate the individual beta n's again in the final estimation. And you see that also, although the criterion, well, forget it. So it works well for the population parameters and for the individual parameters. Now these results were not really fair. The prior that was used to generate the designs was also used to generate the choices. So we assumed we had perfect prior information. Okay, we knew exactly from which population we had data. So we looked for how robust this procedure was for misspecification. So we used the same prior to generate the designs, but then we generated the data from different distributions. So we had an under-specification of the mean. Well, we just add terms. It means that some get positive where they were negative. Sorry? Only 1 minute? You mean 0? Okay. Okay, so this is a robustness study, and of course it works. It still works very well. But this is too small to read. The idea is that this is what I showed you before. The last one is sequential approach. These are root mean squared errors. Sequential approach does best, and then the others. Also, if you have this misspecification, the last one is the smallest, and in all possible misspecifications, the individual approach works quite well. This is for the mean, this is for the covariance matrix, this is for the individual parameters. So I hope I convinced you that it works well for estimating the individual parameters, either the beta ends or the willingness to pay parameters. It works well for the population level parameters, so the mean values and the covariance matrix, how heterogeneous they are, and it's very robust to misspecification. Well, this was basically the content of 2 papers that are recently accepted in marketing journals. So if you look for more information, you should look at this marketing literature. Thank you.
You have time for a few questions?
I wonder, could you go back to the slide that showed your example with the 4 laptops? My question has to do with the difficulty of the task for your respondent. And in this example, you've got 4 comparison products. And you were asking about the screen size in particular. So I noticed, for instance, that the first and the 4th one differ only in the size of the screen. So that's a relatively simple thing. I can decide if I want a big screen or a small screen, right?
Also the battery.
Oh, and the battery size, I'm sorry. But the price is the same, so it seems like a great
okay.
deal, doesn't it, for the 4th one? That's if you want a big screen.
You should switch this 6 and this 5, I guess.
Okay, well, anyway, my general point is that, are you trying to get people to focus on one specific attribute, like
No, not
the
at all.
screen size, in
No.
which case it might be easier to reduce all the other variables. And in any event, it's much easier for the respondent to compare 2 things than make all these much more complicated comparisons among the 4 of them. They've sort of got to integrate something in their mind about the relative value of all of those factors, and that's quite difficult to do.
Well, I guess this is too complicated with 4 attributes. But it's very important that you have different attributes. You don't want to, perhaps I was wrong in explaining the problem. I'm not only interested in the screen size value, I'm also interested in the hard disk value, etc. I'm not only interested in one attribute, so I really want to include several attributes.
But even so, even if you're interested in multiple attributes, I'm suggesting that it might be easier and you might get better data from the respondents if you make the basic task easier for them. Just, do I want this one or that one, a paired
I
comparison.
think you should listen to the next speaker. He'll be
Okay.
discussing very similar. Nico.
In your robustness scenario, did you also consider situations where you not only added the same constant everywhere, but also a completely different vector to your mu?
No, but as the mu is somewhat... Well, here is the mu, so if I add a 1 everywhere or a 2 everywhere, you get a very different pattern already.
Yeah, the reason why I'm asking, probably I'm missing some of the details, but if that were the beta parameters, then if everything only depended on differences of those parameters, then adding the constant would basically vanish, right? So but probably in your situation that is not happening.
No, if we would multiply with constant, then it would vanish somehow, but here it wouldn't. You get very different patterns in the coefficients. And then the choices.
In your simulation, you had there was 3 alternatives.
Yes.
Are they ranking them or
No, they
Just
only have to
picking
choose the
the best?
best one. Yeah. We did something with the ranking, but then not for the heterogeneous market, just for a more homogeneous market.
I'll ask one question. I suppose you have enough choice sets and enough degrees of freedom to estimate the full model with each respondent, or are you just, or not? Is that-
In the end, we have enough choice sets, but not after the first few that were not individualized.
Yeah.
If you only have 4
Right.
choice sets, you don't have enough. That's also why we need the Bayesian approach, just to update the prior, because we can't get maximum likelihood estimates.
But by the time you're done, you could estimate the individual parameters for each individual just from the individual's data?
Yes, but we don't do this because we are mainly interested in the population parameters, and then we need this hierarchical based approach.
Okay. Let's thank the speaker.